So yesterday we discussed about developing a simple estimation models for missing data. So many times the optimization models work very well because we are using the best available information, and the weights are not guessed by any mechanism. Let the optimization decide best ways of finding the weights. So the objective function we just used in the previous exercise was squared error. We can use, as I was telling you, mean absolute error or absolute error, or root mean squared error, and so on. So we can use any of these objective functions to come up with the best form of weights that can be used for infilling or missing data. So one of the things we have to always do whenever we are developing models of any sort, we need to make sure that we evaluate how well we have done. Okay, so if you can see here, this is my estimate and this is my observed value. So I have these two, and those, especially for both calibration period and validation period, I can use information about that. So what is the first step in checking if the model is good or bad? Okay, so what we have to do is we have to get the values together, and probably the first thing we have to do is evaluate a scatter plot between observed and estimated values. That's one thing. Okay, that is given, and we are going to do that. We have done that yesterday to see. So one thing is important when we are evaluating the results of multiple models. Okay, so the problem is that if you have multiple models, each model may be producing a separate correlation coefficient values or other types of errors. So the first graphic we always use for model evaluation is your scatter plot. We do the 45-degree line, that is identity plot or identity line, and then we put observed on the x-axis and predicted on the y-axis generally. So we have those values, and typically if your model is good, the scatter should be around that line, and that indicates that you have done a reasonable job in estimating the missing values. The second approach, the second way of checking is that the error measure, sorry, the performance measures. So we use performance measures, something like R square, which comes out directly when you fit a trend line, right? When you fit a trend line, you get R square. So don't get confused between R square and correlation coefficient. R square is the coefficient of determination, and whereas rho is the correlation coefficient. Okay, so these two are different in a sense that R square tells you how good is the model fit, that is coefficient of determination, whereas correlation coefficient tells you what is the strength of linear association between those two quantities, that is observed and predicted. So in a sense, both of them are giving you how good is the model which you have developed, but there is a subtle difference between these two performance measures. So you have to be very careful and don't get confused one from the other. So in our case, for example, if you are using a scatter plot observed and predicted, and this is your 45-degree line, so your observations can be something like this, not necessarily following the identity line, but your trend line may be somewhere else. So when you fit a trend line, the trend line goes like this. Okay, so the R square value is based on the fitted trend line. Okay, always remember that. So R square is based on the fitted trend line. But one special relationship which connects R square and correlation coefficient. So that is if the relationship you have fitted, okay, if the relationship you have fitted is linear, only when it is linear, then square root of r square will be equal to rho, that is correlation coefficient. So please remember that throughout your career or life, that r square is never equal to rho, or square root of r square is never equal to rho if the relationship is non-linear. It is only equal when the relationship is linear. Okay, so following what I'm trying to say when we are trying to evaluate the visual assessment of our model. Is that clear to everyone? Okay, good. Somebody can say yes or no so that I know that you guys are following.
Yes, sir.
Yeah, because this is tutorial, so I want a little bit of interactive approach, right? So the other performance measures can be, of course, we already talked about correlation coefficient, typically associated with Pearson, okay? So we call it as Pearson correlation coefficient. Then we can also have Spearman correlation coefficient. Spearman's correlation. Spearman's correlation is nothing but a non-parametric version of your non-parametric version. Non-parametric version. So that means it doesn't make any assumptions about the data. So it creates a correlation coefficient based on the ranks of the data. Okay. So you can get this one. You can get this one. You can also get another one called Kendall's correlation coefficient. Okay. This one is indicated by tau, not mu, but tau. Okay. And this one is indicated by rho. Unfortunately, the correlation coefficient is also indicated by rho. Okay. Something is happening. Okay. So all the three parameters are indicated by different symbols, but we can actually calculate correlation coefficient or Kendall's tau. Okay. Now, you can also calculate another very commonly used performance measure. We call it as Nash-Sutcliffe efficiency coefficient. It's very intuitive. You can also calculate that very easily. Pardon me for my spellings, but Nash-Sutcliffe efficiency coefficient or criterion, NSEC, right? This is the one. So this one basically measures your performance of the model with respect to a dumb model. Okay, a dumb model means something which is a bad model. You know, in the absence of any model, what you'll do is you'll fill it with average values, right? So the Nash criteria, NC, equal to 1 minus theta observed minus theta estimated whole square minus theta observed minus theta average. That means your model is now average, right? And of course, you are summing up over all observations. Okay, I'll put an I here, and then you're doing the same thing. I is also all. So basically, what you're saying is that you are going to take a ratio of the differences between the square values of the observed minus estimated by your model divided by observed minus estimated, observed minus average value. That means average value of all the values. So that means you don't have any model. So what you're doing is you're actually comparing how good is your model predictions compared to having no model at all. So if you don't have any other model, so how would be your model efficiency? So that's why it's called the Nash-Sutcliffe efficiency criterion. Okay, but there are other ways of checking how well you have done But these are some of the performance measures you can check, and then make sure that you are reasonably okay. But if you have multiple models, then you have to come up with multiple performance measures. For example, model 1, model 2. Then you can have RMSE, mean squared error, mean absolute error, and so on for one model, and the similar things happening for the other model. Okay, so RMSE, MAE, and sometimes you can use mean relative error. Okay, and you can use this for model 1, and you can use the same for model 2, and along with the performance measures you can use for both of them. So if you have multiple models, if you don't have multiple models, that's fine. You can say that your model performance is good, reasonably good, based on whatever you have estimated. That is the first step. The second step is to check the residuals. You need to go back and check how are the residuals looking. So what is a residual? A residual will be observed minus predicted. So this minus this, without any absolute or anything. This is my residual. So ideally, the residuals, I'm using the entire data, even though we have to check only the calibration data and validation data separately. So we can do that. Hopefully I was able to copy. No, it's not doing that. Okay, let's see. Yeah, doesn't matter. So I'm going to copy all the residuals so that I know. So what are the properties of residuals if you have built a good model? Anyone remembers? While I'm doing this. No? I could have done this one in MATLAB. That would have been much better. Let me do it in MATLAB so that it's much easier. So let me copy this errors, two estimated and predicted values. Okay. The first one is observed, and the second one is estimated. Okay. So here CLC, I'll put it in a matrix format, just in an array. So the first column is observed. The second column is the estimated. So anybody with a clue of residuals, what should we check about residuals? Any idea?
Sir, it should be close to 0.
The summation of all your residuals should be close to 0, or the mean of the residuals should be 0, right? So that's one requirement. The residuals should be normally distributed, but even if they are not really normally distributed, that's fine. And that means departures from normal distribution is okay. It's taking more time. I could have read through the Excel file directly, because there are 7,000 values. So, and of course, anything else?
They should not have any correlation.
Yes, that's basically saying what? Let's take only few residuals. Okay, take only 1,000, so that makes my life easy. When you say residuals do not have any correlation, I didn't understand what are you trying to say. Okay, so these are observed and predicted values.
They should not be correlated.
Okay, excellent. So let me calculate the errors. Observed minus predicted values. So those are my errors. So if I plot the errors, they should go up and down, so they are going up and down. So there is no time-based error structure. So that means as the time is evolving, I'll see more and more errors going up like that. No, I'm not seeing downwards like that. So that is good sign that my model doesn't have a time-dependent bias. Okay, is that clear to everyone? Good. Okay, now let's go to the next one. Since the errors are in chronological order, I don't know, maybe they are not in chronological order, unfortunately, because we have shuffled the data set, I think, if I remember correctly. So we have shuffled the data set, but anyway, I'll go ahead and double check for the autocorrelation, autocore of ER. So luckily the errors, even though they are not in a particular order, there is no strong autocorrelation because they are within the statistically significant bounds. So that indicates that the errors are not autocorrelated. So we have to do that check also. Okay. Now let's look at the distribution of the errors. So we can do a histogram of ER. So that should tell us whether these are pretty close to normal. So the best way to check if data is normal, there are a number of tests we can do. The first test is the histogram. This is a visual evaluation of the data. As I told you, whenever you are looking at a histogram, the number of bins is a problem. So because by default, MATLAB chooses 10 bins. I can increase to 20 bins and see how it looks like. So now we are getting some character of the data, symmetry between two sides we are getting, but of course I don't know the exact number of bins to use. So I can use the thumb rule 5 log 10. So how many values are there? 1070. So 5 times log 10 of 1070. So I should be using around 16 bins. So in that case, I can change it to 16 bins as a thumb rule version, and then I can look at the probability, histogram of the data. So please stop me if you don't understand anything, because this is supposed to be interactive. This is a tutorial. Okay. So now, what is the next one? Anyone knows how to check the normality? Any other ways of checking the normality? Anyone from the audience? You can use your microphone to say. No?
Anderson Darling test.
Okay, so you went into more serious. You went into more serious testing test. Yes, of course, you can use an array of tests. So the first thing we can do is a probability plot, which plots the quantiles of normal distribution and your data. So they should follow on a straight line if the data is normally distributed. So it's kind of not looking very good. Slight departures from normality. They should fall on the straight line. Let's do a quantile plot. That is, it compares the quantiles of normal distribution as well as your data, that is errors. You see that departures here in the beginning and the end. So we would like to see that it follows the straight line. Okay. A typically normal distributed plot, for example, I can generate normal distribution random numbers, norm RND of 2 and 1, and I generate 2000 values. So let's see how the QQ plot looks like for a real normal data. Sometime. What happened? Okay. Oh, I made a mistake. Okay, so instead of generating, I generated too many numbers. I should put 1 there so that H is only 1 value. So now let's do a prompt plot of H. So it's a straight line. So if your data is generally normal, that's the way they should look like, on a probability plot. The QQ plot also should be on a straight line, that is quantile plot. That also looks quite normal without any problem because I generated the random numbers. The other tests we can do is the first one is the Kolmogorov Smear test. So we call it as Kpss Test. Okay. There we typically use the z-score. That means we take the value and you subtract the mean and you divide by the standard deviation. That is a requirement for MATLAB, so I'm doing it for that. Z-score of ER, that is errors, and see, so it comes out to be 1. That means the data is not normally distributed. That means the errors are not normally distributed. But that's okay because that's the that's not the not the end of our model, but it is saying that it is not normally distributed. So the first check would be histogram. Second one would be a QQ plot. Third one would be a probability plot. These are visual, of course. Then fourth one would be you can do a summary statistics. For example, for a normal distribution, the skewness is 0. The kurtosis, the peakness of the distribution is 3. So we can check that information. And these are quantitative. Then we can do what we call the hypothesis testing. The most famous tests are, we have Kpss test, that is Kolmogorov Smear test. Then there is a chi-square test, that is in MATLAB you will be using Kpss test I2GOF, that is goodness of fit test. These are 2 tests. You can also do Lilliefors test. And in MATLAB, it will be Lilly test. And then, as somebody suggested, we can also do Anderson-Darling test. Okay, so we can do all these tests, but of course, it will be an overkill for checking so many tests for normality. But that's okay because sometimes normality check is important because we want to make sure that the data follows normal distribution so that we can apply some certain parametric tests. Okay. The final test for your residuals will be to check if there's any heteroscedasticity or homoscedasticity. Heteroscedasticity means something, the variance is changing with respect to values. Homoscedasticity means the variance is not changing with respect to values. So that means we just plot the observed values with the errors, or we can plot predicted values with the errors. Okay. So I know my predicted values are in the second column. So that's my predicted values. So I can plot D2 on the x-axis and error on the y-axis, and then I can put a red star as my marker. Okay, I can do that. Whoa! So that indicates that there is some kind of heteroscedasticity. That means the errors are going down as the values of the predicted variable is going up. So typically, if a model doesn't have a heteroscedasticity issues, it will be a constant errors. So this one has some problem. It's not a very remarked problem with the heteroscedasticity. So that indicates that maybe we need to do a better job in our optimization and so on. So in that case, we have to go back and check our models, how well it is doing. So in that case, the definition of heteroscedasticity will be predicted value versus error. This is your 0 line. And typically, if there is no variance in your errors, it should look like. But if you see a problem like this, or if you see something like that, so that indicates that there is some problem with your model. and that is called heteroscedasticity. Okay, so heteroscedasticity. That is heteroscedasticity, and having constant variance is called homoscedasticity. Okay, that's called homoscedasticity. Okay, any questions on that? The model development, model assessment, and then model evaluation of your residuals, that is basically residual diagnostic tests. So we need to conduct to prove that our models are good. So you have to do this one for any hydrologic simulation model, not only for your missing data estimation model, for your linear regression model. You have to do it for every single hydrologic simulation model we might be using to double check that all these characteristics are evaluated so that we are doing a good job in developing our models. So if the heteroscedasticity is too much, that indicates that maybe we are not modeling it correctly. Maybe we are missing one variable or the other, or we are doing something wrong. Is that okay? Any questions? Any questions at all?
No questions, sir.
Okay. So the next one is to see how we can apply the same type of concept, but using binary variables so that we can make the selection of your sites. So, for example, you may have some preferences of selecting certain sites for your model. So what you'll do is we can assign binary variables here in the form of, right now we have coefficients here. Actually, the coefficients are themselves working as a binary variables. So they are saying that this is 0, this is 0, this is 0. That means these stations do not have any impact on my estimation, so I don't need them. So that is one way of model telling you that some of these control points are not helping you to improve the estimation. So they are saying, I don't need to use it. But sometimes you have to have control on the control points. That means you want to have some say in what stations can be used. For example, right now 1, 2, 3, 4, 5, 6, 7, 8 stations are used to estimate the missing values at this station. So that means from these 8 stations, you can always try to say that I only want a good number of stations. I don't want all the stations to have to say that how many stations can be used for optimization. For example, if you know that for sure that out of these 8 stations, only 5 stations are good, so we can try to say that tell the model to select the maximum of 5 stations. So that also can be put in the form of a constraint in your solver, right? By using what we call binary variable. So what we are doing is we are actually writing a model like this. I equals 1 to n minimize. This is what our model is. Minimize theta observed O minus theta I estimated whole square. This is what we are doing. Okay, and then the constraints are basically we call it as subjective, and the constraints are theta I m estimated value is the summation of j equals 1 to n minus 1, then the other number of what you call the stations or control points, and lambda j times q j observed times the weight j. That's it. So this is what we are writing. So where this is lambda j is your binary variable. And if you only want the spatial interpolation to use only 5 sites, you can put a condition like this. So if you put that condition, what happens is that the optimization solver will restrict the number of binary variables to 5. So it will only select those 5 stations which provides the best error or the least error, and that can help us to optimize based on the control situation, in this case where we want to control the number of stations we use in our interpolation. Okay, is that clear to everyone? Yes.
Yes, sir. Yes, sir.
Yes, sir.
Yeah. So basically what you do is when you are building your solver model, you can define a constraint here, what I tried to define. So for example, you can go ahead and define, let's say, for example, let me delete these columns for the time being because I don't need them. I know that I have eliminated them. So go ahead, and these two I will delete, and then I go ahead and delete these two, and then I delete these. So basically I'm left with 1, 2, 3, 4, 5, 6, 7. This one also I need to delete, so I'm going to delete that. So I have 8 stations which are now involved in spatial interpolation. So here I can define binary variables. They'll take only 0 or 1. Okay, and I can again define my sum product. Okay, and it needs to be multiplied by, so what I will do is, instead of doing this, I will add another row and then first multiply these two. Maybe there's a way, I'm not an Excel expert, so I'll do this, and then I basically multiply by the binary variable, and then now instead of A1 to H1, I will say A3 to H3. So basically that's what I'm going to use. So those are my sum product values, because I'm doing A3 to H3, A3 to H3 multiplied by A4 to H4, and that needs to be continued till the end. So hopefully it is continued, or no, only going up to some area. So at least we can do it till we get to the point of calibration, at least till 5,000. So we have that estimates based on that particular sum product. Okay, so let's go here, and I'm just going to put it here, and then we can always ignore this error because it's just a. So now we have the binary variables incorporated in our formulation. We have the error also. So I'm going to go to the solver, and we know that we are going to minimize, and the error value is somewhere here, right? The error value is this one, and we want to minimize. Now I'm going to add my constraints. So first of all, I have to say that the other cells are binary variables. So I have to go and say, go up, and then I say that all these variables are binary variables. Okay. Now, these also need to be first defined as a variables. So I'm going to go ahead and add this to the variable list. Okay. So I'm going to add all things to the variable list, so that then it will accept as the These are also as variables. And this one, I'm going to say they are binary variables. So now the solver will know that these are binary variables and it can manipulate them. So now, if I want to say that I only want 5 stations to be selected out of this 8, I can first sum the binary variables. Okay. Let me close this one for the time being. Something I did. This one because I was typing something. Okay, let's go. Okay, so that is good. Close. Okay. Okay, so objective cell is defined. So what I'll do is I'll sum up the binary variables, and I get 8 right now. So I go to solver and then add another constraint saying that the summation should be equal to 5. So I'm forcing that a hard constraint. I'm saying that choose exactly 5 variables or 5 stations. Okay, that's what it is. So I'm starting to minimize the objective function, that is the squared error, summation of the squared error, by changing all the cells. Some of them I have defined as a binary variables, and then I'm only selecting 5 of the control points. I'm forcing the solver to select only 5. So if I do that, then it will start solving the problem. It will try to use only 5 stations because I indicated that it has to use only 5. So what it is doing is it's doing what we call a combinatorial problem, because it's trying to do different combinations of 1 and 0. It'll take some time to get the solution, but it automatically at the end of the whole solution process will get us the best solution that can help us to use only 5 of those existing sites. So sometimes you can define the control sites, you can have that limitation using binary variables. You can also specify a constraint which will say that use only these sites for this season. For example, in some seasons, some sites are better than the other sites for estimation of missing data. So you can use that condition also, where we call it as discrete variables. So we can define that also, and then come up with a best solution to find out what stations are used. So this should finish, but because we have 5 binary variables, it will be checking for a lot of combinations. Hopefully it will end very fast and we should be able to see the solution as we move on. So while it is doing, any questions for me? Should come out very fast. Any questions?
Hello, sir.
Ayushi is asking, is the cluster analysis is
One
same as
question.
this?
Okay.
Tushar,
So somebody is asking is
Tushar, 1 minute. Sir,
no.
Ayushi is asking, is the cluster analysis the same as this?
Okay.
No, it is not. Cluster analysis is different. Cluster analysis is there are 2 things in cluster analysis. One is a supervised clusters and unsupervised clusters. Typically, what we do is we do unsupervised clusters. So typically, the tools we use is the k nearest neighbors. What it does is it first starts with a neighbor and then see whichever has the similar characteristics. It groups them into clusters. Depending upon how many clusters we specify, it will give you that clusters. So that's completely different from this process, because in this process, we are trying to say that we only want 5 control points to be used for our estimation process. So this is the selection process. That is a clustering process. This is objective selection process where we are not trying to put any our own ideas into which one to be selected. We're just saying select the 5 which results in the best optimum value for the problem. Okay, I hope I answered that question.
Yes, sir. Tushar, you can ask. Tushar.
Okay.
Tushar, can you hear me?
What is
Go ahead.
yes, sir. Hello.
Yeah, if you have a question, please go ahead. Yeah, go
Sir,
ahead,
if
ask.
Values are values.
You're breaking up. Probably you might want to type in the question.
You please type the question.
Okay.
You are not audible properly. Tushar, you type the question in chat box. You are not properly audible.
Okay. Any other questions while Tushar is typing his question?
Okay, sir.
Unfortunately, this is taking more time, but ultimately, I can pause the solution and see what is the scenario. So I'll stop it and see what happens. Let's go up and see. So if you see here, it has selected 1, 2, 3, 4, 5. It is still trying to optimize the weights, so it is in that process. But it only selected 1, 2, 3, 4, 5. Okay, so if we allow it to continue for some more time, it will try to optimize the values by finding the best weights and also helping us to find out the best possible control stations. Now, you can use the same technique for different types of problems you may be solving. For example, if you have 3 different choices or 4 different choices in your problem, and let the optimization decide what is the best option for your problem. In the sense, for example, I'll give you something like you're trying to manage stormwater, and then you have 4 options. One is green roof, the other one is infiltration control, the other one is infiltration trench, the 4th one is detention pond, or some other options. And you can put it in the form of an optimization framework within an Excel or any other solution approach, and you can come up with the best possible approach by saying that the summation of all the choices is equal to 1 in that case. In this case, we are now selecting 5 control points. There we'll be selecting only 1 option. So that might give you some ideas for your optimization problems where you're trying to address. So I call it as hydro optimization or optimization within hydrology, because not many people apply optimization within hydrology. They apply a lot in water resources management, which I have applied in both. But I try to bring in optimization within hydrology. Okay. So Tushar, did you finish typing the question?
Yes, sir. Yes, sir. He is asking, what is a fairly good RMSE value if size of our data is very large? That is about 5 to 6 digit each data value. Means he is saying the data values are in terms of 25,550, 23,330, etc.
Oh, you're talking about the RMSE, right?
What will be the fair value of RMSE?
Oh, nobody can say what is the fair value of RMSE, because RMSE is actually RMSE has the same units as your observation, because if you see root, mean, squared, error. So, for example, if you are doing a precipitation estimation and the typical values stay between 0 to 350 millimeters. So if you get an RMSE of 7, that means on an average you are either overestimating or underestimating your precipitation by 7 millimeters. So the RMSE has the same units as your observations, and because you're taking a square root, if it is just a squared error or mean squared error, it will be a different game. But if you're taking a root mean squared error, so that is what you are doing. So in that case, it should reflect, for example, this is what your root mean squared error looks like. Observed minus estimated whole square divided by n, and then square root of that. That is your RMSE. So that gives you a value which is reasonable. If you're getting a large RMSE, let's say you get 100 RMSE for a precipitation problem like this, where the range is between 0 and 350 millimeters. So that means on an average, you are making an error of either 100 millimeters. That means either underestimation or overestimation. So that's not a good model, right? There is some problem with your model. So your RMSE should be within a reasonable range of your values which you are observing. If it is too much, then there is something wrong. Squared error can be any value. It can be big, it can be large, because you are squaring it. Some people even use the 4th power also, or 8th power, because it has to be even. If it is odd, it will have negative values and cancel out each other, and that will not work in our optimization. Okay, good. Any other questions?
No, sir.
Okay, good. So similarly, we can develop what we call the streamflow forecasting models, which we started yesterday. So for example, this is our streamflow values, and we noted that there's a very strong persistence, and then we can use same multiple regression concepts to develop what we call a nice streamflow forecasting model. So again, we do the same thing. We provide the lagged values of inputs, and then we develop our streamflow model. So if we can do it with stage, or you can do it with actual values of the discharge. And as you notice that there is a strong relationship between discharge and stage, typically a nonlinear relationship. So for example, I can show you here. I think there was a gap here. I don't know what happened. Oh, okay, it put zeros there. Okay, so so this is a typical nonlinear relationship, and I'm going to show you here. I'm going to paste it here. Oops, paste special values because these are converted to meters. So this is my discharge. I'm going to paste it here and then plot both of them so that you can see the nonlinear relationship between stage and discharge, which is called the rating curve. Right. So already we have a model. So sorry. Insert and then just use. So as you can see, it's a nonlinear relationship. So either we can build a model between stage and discharge, or we could use previous stage values to predict discharge, or we could use previous values of discharge to predict your discharge. So that means you basically have Qt is a function of Qt minus 1, Qt minus 2. So Qt is nothing but W1 times Qt minus 1 plus W2 times Qt, Qt minus 2. So you can have a model like this, and then you do the same procedure what I have just indicated. You take the two weights, you put it on the top, and then You estimate the values, you square the errors, sum up the errors, use optimization to estimate the W1 and W2 values, which we have done, I think, yesterday, similar to what we have done for this precipitation estimation problem. So we can do that. Okay. Now, I'm not sure, is anybody familiar with artificial neural networks in this group right now? You can say if you are familiar.
Yes, sir.
So a lot of,
Yes, sir.
sorry?
Yes, sir. Yes, sir.
Okay, so a lot of students are familiar with I would say majority of this, or so we can try to
Many, sir,
reduce the
many.
many. Okay, so many are aware of artificial neural networks, and I'm assuming everybody knows how the whole thing works, and you can develop artificial neural networks within Excel also. So if this is Qt -1 and Qt -2, and you can incorporate the connections between all of them, and then you can develop your artificial neural network. So the best way to do is that you assign the weight, W1, W2, and so on. You put another bias term here, and then assign weights to, say, W01, W02, W03, that is the third one, and W04. So 4 weights which are coming from the bias term, and then you have all the weight, and then you write your sigmoidal function activations. So that means whatever is coming inside will be, let's call it as capital A, whatever is coming out, weighted input capital B, weighted input capital C, weighted input capital D, and whatever is coming here, the weighted input coming as E. So once these come in, then you can activate through sigmoidal functions. Either you can use a tan hyperbolic function or a sigmoidal function. Sigmoidal function is pretty easy, 1 plus e to the power minus x. So this A will be here, and that will come out of here. If it is B, it will come out as B, C, and D. That in turn will get weights, the final layer, 2, 3, 4, and then they again pass through another final sigmoidal function. So once you have that, then we can set up this whole thing in an Excel. And even though it's not the best way to solve artificial neural network problem inside an Excel, but still you can estimate the weights, and you can develop a reasonably good neural network forecasting models, because the weights can be optimized by the solvers. Of course, the solver using the technique of optimization may not be the best, because artificial neural networks are trained by different algorithms. For example, the backpropagation algorithm, then there are variants of backpropagation algorithm, and so on. So in that case, you will notice that the performance of the neural network you might have developed using Excel might be slightly inferior, because there is a chance that the solver might end up in a local optimum solution as opposed to a global optimum solution, as it is possible in other softwares. So MATLAB also offers artificial neural networks. MATLAB also offers now deep learning, so that might be useful for large-scale prediction problems, as well as big data functional approximation problems. So here we are using only one neural network, one hidden layer, but you can use multiple layers to improve the forecasting capability of your neural network, especially the time series forecasting. So I'm assuming that everybody knows a good amount of artificial neural networks. They can actually develop the I close this. Where is this? So you can actually develop a neural network model using let's see, where is my solver thing? Somehow it isn't As soon as I click on that, it's just going away. Okay, let me see if I can get solver. Okay, close. So that can be developed. So any questions or clarifications that you yourself can develop a neural network model pretty straightforward in Excel if you want to, but of course you have other tools to develop neural networks. Okay, is that good?
There is one question, sir.
Yeah.
In this case, like time delay networks, do we require dynamic or static ANN?
Depends on the adaptive level of forecasting you are doing. So definitely, if you have new data coming in, then probably you have to use the dynamic nature of the neural network, where there's a chance for retraining, and then come up with a model which can help us in using the new information to improve the forecast. So it's more of a adaptive forecasting, what we are talking about. Right? Any other questions? Any other questions for me?
Sir, no question at present.
Okay, so good.
Yes,
Thank
sir.
you.
There is one only.
Yeah, go ahead.
She's typing.
Okay.
Yes, I will see. You can unmute and ask.
Yeah.
Yeah, she has written, data-driven techniques are used a lot in inflow forecasting. How good ANN is?
Okay, so there are a few things we need to be very careful with your streamflow forecasting in streamflow forecasting using artificial neural networks. The first one is that if you're purely working on persistence, that means purely univariate models may not be a good option for doing a prediction. For example, if you're just using qt minus 1 and qt minus 2 as your input, so your model is kind of short-handed because it is purely relying on two univariate inputs which have some good correlation with the existing one step ahead value. That's fine, next value. But the problem is that unless you put some causative data, causal variables. What are causal variables in this case? In this case, it can be rainfall T minus 1 and rainfall T minus 2 or rainfall T minus 3. Sometimes base flows published in Journal of Hydrology, where we were looking at different error measures. We developed a new error measure. So in that case, just to demonstrate the streamflow forecasting model, we were using base flows. I think it's in the Tapi River basin, published with Dr. Sharma and Dr. Patel. So we were using the base flow values also to improve the prediction. So base flow is kind of a causal relationship, because sometimes base flows delayed can be contributed to the stream flow. Rainfall contributes to stream flow, and then finally the lagged values of the stream flow itself will contribute to predictions in the future. So in that case, if you are planning to develop artificial neural network models, things can improve if you include more causal information, right? But for flood forecasting purposes, you may not need that much accuracy, because you're going to use it for generally operational decisions. So if your forecasts are within a specific range, if you're able to produce the stage value reasonably okay, So for example, typically what we do in data-driven models in case of stage forecasting, if this is a river and you have data here and you have data here, and this is the point of interest because there is a city downstream. So we could link the stage here and the stage here and develop a one step ahead forecasting model, which works very well because the only part which is influencing is the channel, the routing part. So if you know the stage value, we can accurately predict what might happen at stage value at B. So that might really help us in replacing the routing models and using data-driven models in that case. So again, it depends on what is the purpose for which you are using the data-driven models. Sometimes the data-driven models may not understand purely based on lagged information or highly correlated information. They might need more than highly correlated information to improve forecasts. Okay, I hope I answered your question.
Sir, she is asking, is there any practical application of ANN forecasting? I mean, real field use of ANN.
Yes, in many agencies they use some form of data-driven models for forecasting because they have a lot of data, and they are used either as a base model, that is a model with which they can refer to other models whether they are doing a good job, or they can be used in real-time forecasting because it is a very quick turnaround. They need minimum amount of variable values or other types of variables. For example, if you are looking at a hydrologic simulation model, it requires all the related Muskingum parameters for routing, or it requires other parameters from the watershed to run the hydrologic simulation model. So in that case, data-driven models are cheap and simple, and they can give reasonably good results as long as some causal information is incorporated into the model. And they can be used for real-time forecasting. And in many places in the world, they do use regression models, not even neural network models. They use simple regression models. They use stepwise regression models to eliminate the variables which they don't need. And then they use neural network models for short-term prediction, especially for emergency operations as a guidance, not necessarily as an exact value. If a neural network model is telling that tomorrow's stream flows will be in this range, that can be a good forecasting model. The other areas where they use data-driven models is that in case of short-term operations of reservoirs, they run the data-driven model, they get the forecast, run the optimization, get the new set of operational schedule, and see how well they are doing, because there's a little bit of problem there, because there's no need to worry about the amount of storage they have is so vast they can manipulate if the system changes a little bit. So small errors in your data-driven models, if they don't affect the system that much, if they help you to make decisions, they are good models enough. So there are a lot of places where they are using neural networks model. I developed my first neural network model in 1995. So we did a 10-day forecasting model for rainfall. That was the first application at that time, probably beginning of the applications of artificial neural networks. Then I have multiple places where I develop neural network models, not necessarily to use them completely as a full-time models, but as a base models or a models for using in adaptive forecasting. The other one I used is to see if there's any help in classifying the stream flows into geometric patterns and then feeding them to artificial neural networks. So, as I said, in many real-world applications, we have artificial neural networks used, and we have that. Any other questions?
Yes, sir. There is one more question. how to check autocorrelation for a combined network of rain gauges or stream flow and not just for one gauging station.
When you say combined, I don't follow. Okay, so maybe I'm not following the question, but there's no way of combining data when you're trying to find autocorrelation. Autocorrelation refers to as one single time series, which is with respect to time at one site. So, for example, here is an example I'm going to show you. This is the rainfall time series, which is provided by Dr. Sharma in, let's say this is Ahmedabad. And we have monthly rainfall data from 1901 to 2000. Maybe there are some holes in between, I'm not sure. But looks like it is. There are some, there may not be any gaps. Okay, so this is 88. Maybe some gaps also, I'm not sure. But anyway, so this is your one single site, what you call monthly precipitation data. So let me see if I can put it in rainfall. R equals. So this is your monthly rainfall data series. Do you expect autocorrelation? Anyone? Or no autocorrelation?
No autocorrelation.
One person says no autocorrelation monthly. Any other ones agree with the first person? Well, let's plot the autocorrelation and see whether there's autocorrelation or not, right? Autocor of R, that is rainfall. So what do you see here? Do you see autocorrelation? A decent amount. It's not very strong as stream flows, but there is a monthly autocorrelation and you can see the cycle. So seasonality, that means every 12 months, the maximum value of autocorrelation happens. That means you have high amount of rainfall in 1 month, which happens every year. So probably that is in June or July, whenever you have the maximum rainfall in Ahmedabad. Is that good? Clear? Yes?
Yes, sir. Yes, sir.
Okay. So let's say, for example, you are interested in trying to find out if this particular time series has any climate change signature. Okay. So what would you do as a first step? If I want to know if this Ahmedabad rainfall, monthly rainfall series, does it have any climate change signature? So the first thing is I need to plot with respect to the years, right? So I know that there are 1,224 values. So I'll just put a K. Doesn't matter whether I use the monthly values. 1, 2, 2, 4, right? 1, 2, 2, 4. Okay. So I just created an index for that. Now I'm going to plot K, uppercase, lowercase k, and then transpose of that, and then the R value, and then I'm going to use a symbol R star. Okay, so I'm going to just plot the scatter plot with respect to time. So this is time progressing, and then we don't see much of a trend. First of all, the problem is because of the cyclic nature of the time series, it's very difficult to find any trend. So let us put a LS line, that is least square line, on that to see if there's any trend. So I don't see any trend excepting a straight line. So would you agree that there is no trend? Okay. At least visually it says there is no trend. Okay, so now how do we check if there is any trend by using either parametric tests or non-parametric tests? So the parametric test is basically fitting a linear regression line and checking whether the slope of the line is statistically significantly different from 0 or not. That is the one way of checking. It's called parametric test, right? Parametric test is we have to define a null hypothesis and an alternate hypothesis. Null hypothesis says that the slope of the line, let's call it as theta, is equal to 0. And the alternate hypothesis is the slope of the line not equal to 0. This is what we are going to check when we are doing what we call the regression line with respect to time. This is time at the x-axis and the rainfall on the y-axis. We fit a trend line, and theta x plus c is your equation. Y equals mx plus c. So in a parametric test, we actually test this condition, null hypothesis and alternate hypothesis. And how do we check that? Because we know that the statistic value follows a t-distribution. We can check using the t-test. Now, the results of that parametric test are provided by Excel or MATLAB or any other software to say whether this theta, the slope, is statistically significant from 0 or not. So the other easy test is the Spearman's rank correlation test. So time R. So remember, there are 3 different correlations. First one is the Pearson correlation. The second one is the rank correlation, that is Spearman, which is based on the ranks of the data. So that means whenever you are ranking the data or providing ranks to the data, there is no assumptions involved. So therefore, it is a non-parametric test. So Spearman's rho SR test is a non-parametric test. Okay, it's a non-parametric test. So how can we do that? We can quickly do it in MATLAB, for example. So let me go here and say rho. Let me first check the help on COR. COR means correlation. Okay? And it will tell you the use of the this thing. So we can use this way. Rho and p-val, right? Okay, so rho, that is the correlation coefficient, and p-val, you can put anything actually, I'm just putting the same thing what MATLAB is putting. P-val and core between the time and the rainfall value, and the type, we say type is Spearman, so we type Spearman. Okay, so I'm basically doing a non-parametric trend test on the rainfall data series, the monthly rainfall data series, to appreciate whether there's any trend or not statistically. So if I press enter, oh, okay, so okay, I need to transform this into another variable, so let me put it as K-Bob. Okay, so let me put this as J. Oh, I put this. Okay, that's the reason. Okay, so J and R are now available. So what it is telling us, the correlation is very small, 0.047. That means pretty much random data. There's no correlation between time and the monthly rainfall. And the p-value is so high, indicating that null hypothesis is true. So indicating that there is no trend. Does everybody follow that? If this p-value is less than 0.05, because we usually do tests at 5% significance level, so that is, we can say that there is a trend if it is less than 0.05. There are 2 things which are telling you the story. One is the correlation coefficient. Spearman's correlation coefficient is very low, indicating that data is completely random, and the p-value is very high. That indicates that there is no trend in Ahmedabad rainfall data, monthly rainfall data. Is everybody clear about that?
So, sir, we conclude that this data is free from climate change impact. Is it?
This is one test for us indicating that there is no trend, first of all. The other way of doing this is that we can split the data into two halves, the first part of the century and the second part of the century. So if we copy this, we can divide that into two values. I could have done it in MATLAB also, but let me do it here. So what is the half of 1224? Approximately. Doesn't have to be half, but 600 and something. What is half of 1224? 1224 divided by 2. Oops, sorry. 610, 612. Okay, perfect. So let's divide this into two data sets, the first half of the century and the second half of the century approximately. So put it in F value, D of 1 to 612 of the first variable, and D of 613 to second variable. Sorry, am I putting it right? Second column. Sorry, 613 to 1224, and the second column. So that should give me the second. 612, 1 to 612, 613 to 1224. Am I doing something wrong? Oh, this is 1 again, sorry. What? Oh, this is not D, sorry, R. What am I using? I'm sorry, I'm tired. Okay, so R. So these are the two data sets, one coming from the first part of the century and the second one coming from the second part of the century. First of all, let's look at the box plots of these two. So I'm going to look at whether there is any significant difference in their two distributions. Not much. The median values are very well, but of course the interquartile range is higher in the second part of the century. Let's look at the case density, that is the smoothened histograms of the first one and the second one. That is how it looks like because it is monthly data. And I plotted on top of each other. So any changes? Can you see something? Or maybe it's overlapped. Let me put a hold on. So I have these two. So you can see pretty much not much change in the distributional characteristics of both of them. Agree? A little bit of higher density in the beginning, but more or less they are following the same thing. Any feedback on the visual observations of the two data sets, the first part of the century and the second part of the century? What else we can do to check there are no changes in the Ahmedabad rainfall? Of course, we are looking at monthly rainfall. We might even look at annual maxima also. We can do annual maxima and see if there are any trends in the data. Right? We can do that. So any other thoughts? Let's do a Kolmogorov Smear test, a two samples Kolmogorov Smear test to confirm that the two distributions are coming, or two distributions are coming from the same population. Okay, so let's do Kpss Test 2, that is Kolmogorov Smear test 2 samples. So logical 0 indicates that it is basically they are coming from the same population. So that means the first part of the time series of Ahmedabad monthly rainfall values and the second part of the Ahmedabad monthly rainfall values have not changed at all. Okay? Is that clear to everyone? Yes. Any questions?
Yes, sir.
Yes, sir. 3 questions.
Yes.
Sir, Tushar.
Okay, go ahead.
We'll come back to you.
Okay.
The first question is, what are the steps to check effect of climate change in 30 years precipitation data? And there is one more question, that shall we do homogeneity test for change point analysis?
Okay, very good questions. If you have 30 years of precipitation data, okay, first of all, are you interested in annual maxima, that is block maxima? So you need to find out maximum value every year and see whether the precipitation extremes are having any trend or not. Let's say if you are not interested, I mean, most of the time we are interested in precipitation extremes because that is what drives our floods. So we should be more interested in precipitation extremes. But if you are interested in regular precipitation series, in this case, like annual values or regular monthly values or daily values, in that case, you have to still look for any long-term trends in your 30-year precipitation data. Now, precipitation data may have seasonality, what we have seen just now, because the same high values repeat in the same month every year. It's not a cycle, so there is a difference between cycle and seasonality. So hydroclimatic variables like temperature and precipitation will have some seasonality. So in that case, you have to check if there is any seasonality. If there is a seasonality, then you have to do multiple tests to see if there's a trend consistent, trend with seasonal, trend considering the fact that the data has seasonality. Okay, so there's a man-candle test available in MATLAB. You can go into use this group of MATLAB. There are a couple of codes developed by United States Geological Survey. One for accounting for seasonality. So you can use that to check if there are any trends in the 30-year data. Okay. You can also do Spearman's row test, which we just did, to check the trend. Now, Spearman's row and man-candle test are two different animals because Spearman's row basically checks for the correlation between time and the variable. Man-candle also kind of checks in a way the correlation between the time and variable, but the way the correlations are calculated are different in man-candle's tau compared to Spearman's row. But both of them will report a possible connection between time and variable value, because as the time increases, the variable value is increasing. That means there is a trend, right? So both of them will tell there is a trend in your data. The next step is to see if we can split the data into multiple blocks and then see if the characteristics of the two data sets or three data sets are similar. For example, we just split the data into two blocks. And recently we published a paper on stationarity in Journal of Hydrologic Engineering. You can check that paper. That has a lot of ideas for you to see how we can check the stationarity of a time series, in the sense if there's any trend or not trend in that case. So you can also check whether these two blocks have similar statistical properties. Okay. In this case, I have checked whether the distributions are similar. Okay. Now, unfortunately, this rainfall data, what we are looking at, is not normal. So, for example, I can check the probability plot, and you will see it is not at all normal, which we have already seen from our case density plots. The second one will also show that. So there is a problem. And there are a lot of zero values. That is another problem for us because we cannot do any reasonable transformation. So the other way around is we add a number to it and then we do the transformation. That's also possible. Since not going through that much effort of trying to establish normality and doing the parametric test, let's do a non-parametric. All I have to do is I in MATLAB rank sum of f of 1 first block versus second block. So let me see the help on rank sum so that I can put the p-value and all those things. So it is a p and h value. So let me see if I got the rank sum f of 1 and f of 2. So here you can see that the value is very high and the h value, the null hypothesis, is true, indicating that these two time series do not have any statistically significant differences in terms of their medians, because non-parametric tests are based on ranks. It is telling us that your Ahmedabad data has no climate change signal ever based on a preliminary set of tests we have done. We have done distributional checks, we did the trends, we did Mann-Whitney test or rank sum test using 2 different blocks. You can try 10 different blocks and try if their distributional properties are changing. Actually, we can plot the entire data and see if something is changing with respect to time, which we saw that nothing is going on in your data. So that tells us that your data set, unlike your other data sets, is telling us there is no trend. But for example, if you take the maximum annual stream flow at, we have different Narmada and Tapi River, for example. I'll take the Tapi River from 1974 to see if there's any trends in the data, and we can check what is going on with the data. Okay, I'm going to put that in Q, and then I'll plot Q, just plotting Q. So what do you see in the Tapi River maximum annual flow without even going through anything? Anyone?
It is decreasing.
It is a decreasing trend, we can see visually. So let me create another time variable for it. T equals 1 to 44 values, right? So let me see if I can plot them with respect to time. T comma Q comma R star. Okay, so a red marker. So that indicates a decreasing trend. So let me do a LS line, which also is a parametric line, which tells us there is a trend. So quickly, let us do an SR test on this one so that we can prove that the trend is there in your decreasing trend in case of your Tapi River. So let me go ahead and use my old command, COR. Okay, go and change to T bar, and then this is Q, and then Spearman. So what do you expect? Do you think the Spearman rank correlation test will tell us that there is a decreasing trend? Anybody want to guess? No? Okay, I'm going to push the button now. Okay, so what does that tell you? Negative correlation indicates there's a decreasing correlation with respect to time. That means as the time is increasing, the variable value is going down, indicating a negative trend. And then the p-value is much less than 0.05, indicating statistically significant trends when we are trying to establish the Spearman's rho. So the values of, which one did we take? Tapi at yearly, is that the site? Yes, yearly indicates decreasing trend in your stream flows, maximum values. So there is something going on in that stream where the values are going down. It can be climate change, or it can be withdrawals from nearby city, or it can be decrease in the precipitation. We can find out the causative factors after we investigate. Now, for the second question, sorry, I forgot the second question. The first question is 30 years of precipitation data. The second one was the homogeneity.
Shall we do homogeneity
Right?
test for change point, or how to check change point of train?
Okay, the first thing is that when you have a time series, you can check for before you check for homogeneity. This is a chicken and an egg problem, because sometimes the homogeneity can tell a change point can tell homogeneity is there or not, or the other way around. So the first thing is that find the metadata about your data. In the sense, try to find out everything about your data. Has the instrument has changed? Has the location of the instrument has changed? The measurement process has changed? If nothing has changed, so there is no need to suspect any homogeneity issues in your data. So the data is coming from the same source. It is measuring the same process over the time without any problems. So now, if you eliminate from the metadata that there is no homogeneity issues, then you can take the data and then try to evaluate. You can pass it through a change point test, and change point can be one single change point or multiple change points. If the change point test gives you one point, that means at one point it feels like the time series has changed, use that as a breaking point to see the statistics before and after, to see what might be the reason why a particular time series is experiencing a change point. If there are multiple change points, again do the same thing. Try to attribute it to one potential reason why there are multiple change points, either operation of your, if it is precipitation series, then it's completely different. We have to identify what might be the reasons why there are change points. It can be a shifting in the mean because of climate change, or it can be some other reason. But if it is stream flows, maybe urbanization, water withdrawals, diversion schemes can provide a change point test, or including construction of a reservoir. Good. I hope I answered the question.
Sir, Tushar is asking how to find spatial correlation between stream flow data in a river network. That's a totally different question.
Partial correlation, you said?
A spatial correlation between stream flow data in a river network. I think he wants to ask that if the data is for two gazing sites, then how to find out?
It's more of a cross correlation, right? That's what you were saying.
Yes, I think so.
Yeah.
Is it
so? It is
cross?
It is cross correlation when you're talking about multiple. Yeah. It is cross correlation if you're talking multiple sites. So that means that two sites can be correlated with each other by zero lag. That means both of the time series are exactly at the same time, or one is lagged and you see a stronger correlation. So that means one series is always lagging behind, maybe for example, an upstream station and a downstream station. So in that case, there is a lag between the flows between the first and the second one. So that indicates that there's a one time interval lag. So that can help us to see, that can help us to build what we call cross correlation models and develop better prediction models for stream flow forecasting. And that can be done. For example, in MATLAB, we have, if you have the what you call econometrics toolbox or signal processing toolbox, it automatically does the correlations backwards and forwards with the different lags, so that you will know exactly where the cross correlation is the highest, and you can use it for your forecasting purposes. Okay, good.
Yes, sir. Thank you, sir.
Sir, one more question.
Yeah.
That is from Professor Sudhanshu Dikshit. How to check for change point of trend?
Change point of trend. Okay, so that's again a little more complicated process. Like it's a similar way you are checking for any data set. So the change point exists in your, if the change point exists in the data, it's very unlikely that the trend will have a change point unless there is a shifting mean. That means there is a whole concept of shifting mean models. That means the mean stays at one level and has a trend for some number of years, and then again there's a shift in the mean. Again, you'll have the same another trend. So if there is a trend, if there's a change point in your time series, it's equivalent to evaluating trend before and after the change point, and that indicates that there is also a difference in the trend before and after. The other thing is that if you were to do a parametric regression before and after the change point, you can actually compare the slopes of these two lines. There is a slopes test which can help to compare the slopes of these two lines. Then you can say that the trend before the change point and trend after the change point are either statistically similar or they are different. Okay? Hope I answered your question. Any other questions?
Sir, shall we do ITA? That is, I think, innovative test. ITA method also using the same technique.
I'm not familiar, unfortunately, but should be possible. I have not used ITA till now,
Right.
so I don't want to comment on something I have not used. But I think, see, the change point analysis is a little bit tricky in the sense that change points are only statistically significant unless the time series poses that that kind of behavior, in the sense there is exactly a change which can be easily noticeable through the visual evaluation. So so we have to take with a pinch of salt if a statistical test is telling you that there are change points. Okay, I'm not saying we should not trust the change point test results, but every type of change point has to have some kind of attribution attached to that. And change point tests can give different results if you have small set of samples or less number of years. For example, if you have only 44 years here, okay, so that might not give a complete picture of what is going on in this particular time series. So for this Tapi River, if I were to extend backwards, if somebody, luckily I have data from 1900s, then maybe there's no long-term trend in this particular river. Or there can be a trend in this river that can be linked to a causative factor like precipitation. So we need to check that one. So that is my suggestion on the change point test. We did not rely much on the change point test for stationarity assessment. Our idea was to use multiple non-parametric tests by randomly creating blocks of data and checking one against each other. That is what we did in one of our papers, where we are testing different types of approaches for evaluating stationarity of any time series. So one important caution I want to make is that stationarity is not the property of your time series. Stationarity is a property of the process which is generating that particular time series. So that means a time series is a surrogate of your process. A process, for example, a rainfall generating process is there. Rainfall is being generated by a specific type of event. So you are not checking the stationarity in a sense of the time series. For all practical purposes, yes, but in a sense, you are checking the stationarity of the process. So if you know that the process is generally stationary, your time series will also reflect that. And remember, time series is only one sample or one slice of the whole process. You don't have the whole population. So you only have a sample which you are trying to infer from the sample about the population. Okay. Any other questions?
Yes, sir. There are two questions. One question is, yesterday you have discussed about gridded data. Is there any open source tool for reanalyze gridded data into finer resolution or in coarser resolution?
Unfortunately, there is no. So the only way you can generate your own gridded data is to redefine your grids and then do some kind of simple interpolation and rechecking whether you are able to do a good job with respect to a ground truth. So for example, this is your coarser resolution gridded data, and you want to go for a finer resolution of this size. Okay, so I'm going to draw with another color, say probably that one. So, and then we are talking about the smaller grids. So what you would do is you will start with the bigger centroid, that is the centroid of your bigger cell, and then you identify the centroid of the smaller cell, and you can either fix the value of this one based on the distance-based interpolation with the other centroids of the big ones. So there's another big centroid, there's another big centroid, big centroid, big centroid, big centroid, and then interpolate to that smaller grid location. And of course, these are further from this red point, so they'll have low weight, but still you can interpolate to the smaller gridded cells, and you can generate your smaller gridded data sets. Once you generate your smaller gridded data sets, you can compare with ground truth if you have any rain gauges or any other sensors which are measuring that variable, and double check if you are trying to do a good job when you are downscaling your data, spatially downscaling. In the similar process for spatially upscaling. So there are different methods. For example, Shepard's method is there, which is we worked on some gridded data set. We published a paper in International Journal of Climatology. A conceptually superior Shepard's method for development of gridded data. So in that case, Shepard's method was used instead of inverse distance weighing method to generate gridded data and have more finer resolution gridded data, and use it for a specific hydrologic simulation model the student was interested in applying to. So yes, you can do it, but unfortunately there are, if it is one set of data, you can do it using ArcGIS, or you can do it for you can automate the process using Python in ArcGIS or QGIS. You can try. If you are doing a simple interpolation using inverse distance or Shepard code, define the new centroids of those small grids, and then quickly interpolate to those values. Okay, I hope I gave you some answer for your problem.
Yes, sir. Yes, sir. There is one more question. What are the latest method or approach to check trend, as good journals don't accept paper using Kpss Test and other normally used tests?
There are no no advancements in trend analysis tests, but if it is a non-linear trend, there are some assessment tests, because Mann-Kendall actually test the monotonic trends, in the sense that they can be linear or non-linear also. The only issue, when you, let's say when you write a research paper, obviously the reviewers are looking for some interesting feature of your study, in the sense, okay, trends are there in your particular data set, and there's nothing wrong in using readily available trend tests. Nobody's going to it's a bad work. But the problem is the establishment of the attribution factors. Why the trends are happening? What's the reason for that? So for example, if you're evaluating streamflow trends, maybe you should also concurrently look into temperature trends and precipitation trends in that region. So that means maybe temperature is the one which is responsible for changing trends in streamflow as opposed to precipitation. Maybe precipitation doesn't have any trends. So it's more of the physical basis of the problem as opposed to statistical tests. People are not really concerned about new statistical tests for trend analysis. People are more concerned about how you pose the problem and how you explain the problem and how you try to decipher information from the existing variables and how you can try to provide causative information and how you can provide some interesting intuitive information provided on the physical basis from your region. That is what is important. So I don't see any new trends tests other than there are a couple of tests, I don't remember the name, but looking into non-linear trends in a very absolute sense, in the sense that yes, there are non-linear trends between the time, there is a time and the variable, the trend is non-linear, like an exponential or some kind of a trend like that. So how do we, so that is one thing. So if your trend test is mainly to confirm stationarity, then it's better to do all kinds of tests on the side to make sure that the time series in fact is stationary based on the strong stationarity concept or a weak stationarity concept, distributional checks, changes in the 4 moments, for example, 1, 2, 3, 4, those kind of tests needs to be done. So that's what at least my current knowledge on how the trend tests and the climate change groups are going. Okay.
Sir, there is one more question.
Mm-hmm.
For soil data interpolation, which method is preferred, IWD or Kriging?
Okay, that's a very good question. Well, there are a number of issues with interpolation. So the first one is, if you are looking at soil data, first of all, you need to plot a variogram. Okay. So a variogram is a relationship between the distance between the points versus the variance. That means the difference in the values squared. You can half it, it's called semi-variance. And then variogram must be plotted. So in the first lecture, I showed you the variogram of rainfall data versus radar data. So if this variogram has some structure which can be fitted with one of the available acceptable models, for example, Gaussian or spherical or exponential models in Kriging, then you can proceed with Kriging. But Kriging can sometimes produce negative values, which if you don't want them, that's another problem with Kriging. Kriging has a lot of assumptions to be satisfied, so that's another issue. Ordinary Kriging is pretty straightforward, but I would recommend first start with inverse distance and see how well you are able to replicate the values with the ground truth if you have ground sensors in an area, or some other mechanisms of testing how well the interpolation went. And then the second one is try to use another technique. There are other techniques, like, for example, thin split splines, then you can use trend surface models, both global and local polynomial models. Then you can use a variance of inverse distance methods. So you can exhaust some of those potential interpolation schemes to see which one performs better. And if the first one, the inverse distance, performed reasonably well, then you don't have to justify using Kriging unless the inverse distance fails miserably, and then kriging can perform very well. Remember, kriging can perform very well if your variance structure is good enough to be modeled by one of the variogram models. Those are authorized variogram models, and they are called, this one for example, Gaussian or exponential or spherical, and so on. So I think I would say first experiment with simpler methods, see how well it is. If it is absolutely bad, then increase the complexity. That's what my suggestion. Okay. Any other questions?
No more questions in chat box, sir.
Okay, that is good. So how are we on time? Where are we? We still have time?
Some 10-15 minutes, sir. 10-15 minutes.
Okay, good. So, as again, when you are looking at the frequency analysis, what we talk about for design floods and so on, whenever we are trying to do the frequency analysis, first of all, we need to make sure that non-stationarity. So if there is a trend, then developing a design flood from that particular data based on historical data is a little non-defensible. That means you cannot defend that, because you cannot say that this will be a 100-year return period based flood or so. So that itself is a little complicated proposition when we want to say a stream flow based frequency analysis. So if there is a trend, then we cannot conclude a specific value for a 100-year return period. That requires you to evaluate the changing nature of your parameters of your distribution. Okay, so unfortunately, for many of our time series, we may not have any time series. For example, here we may have from 1966 some data sets. So, for example, if I take this data set from 1966 and see if there's any trend in the data, that kind of helps us to do some assessment of whether we can go for the frequency analysis or not. So, for example, let's plot the data of S. So this one seems to be reasonably okay, and this tells us that yes, there is a variance change, but pretty much this one doesn't have any trend over time. So even though it's a tiny slice, approximately 1966 to 2000 something, so we may have some, how many years of data we have? Around 51 years, which is a good sample size. So in that case, our frequency analysis suggests that we can probably fit a distribution to this data. So for example, let's check what distribution this data follows. Now, since these are annual maximum values, probably we can apply logarithms to this data. And then that looks approximately log normal. So we can fit, let's say, we can do a Kpss test on the z-score of our log transform data. And it shows that it's a normally distributed data, that is log normally distributed data. So now we can always fit a we can always fit a log normal distribution to your data, and then try to make predictions about 100-year return period at the most. You can only make predictions, or at least estimation of 100-year return periods if you have a bare minimum of 50 years. So typically, double the return period, you can make some kind of assessment. If it is less than that, then even 100-year return period estimation itself is very uncertain territory, and in that case, you may not be able to do that. So that's the important point we should recognize. So some people will say that we can still do frequency analysis as long as the trends we are looking in the data are minor, they are not that significant. For example, I can take the last time series and see what is going on with this one. So if the trends are not that significant, then probably we can probably use the constant stationarity assumption to do the frequency analysis. So otherwise, we have to do a little more complex analysis of trying to find out how the frequency analysis can be defined in a non-stationary environment, which is a completely different exercise altogether. So let's see how the Y value is looking in this case. So this one is also seems to be a reasonably well-behaved time series. Doesn't have any trend. Let's do for the process of confirmation. Let me do a SR test. Then so R and P values. Let's go ahead and get the R and H of transpose and Y, and then type Spearman. So the R value is almost close to 0, indicating it's a kind of random data. And then it is also telling us there's no trend at all in your data based on high value of P value. So this series constitutes a good series for our frequency analysis. Of course, we can do a what you call runs test to see if the data itself is a randomly assembled data with no correlation. So run test tells us it's random data. So that's good for frequency analysis, especially statistical analysis. We can also look at the autocorrelation if there are any sequences of high flood years, and this basically tells us there is no significant or not at all almost any autocorrelation in your time series. So that means the annual block maxima of this particular river, which are collected for the last 51 years, and these values are completely random by all kinds of tests, and they are stationary, we can happily do frequency analysis for this one. So you don't need more than, for example, you can still do more tests on stationarity. For example, in time series analysis, there are two tests. It's called Kpss test, and there's another one. I'm drawing a blank on the acronym, but you have a couple of more sophisticated tests to prove that a time series is stationary. We have used in our paper to show that. So once you use a barrage of tests to prove that a time series is stationary, then evaluating frequency analysis or doing frequency analysis to estimate a n-year return period flood is acceptable, and you can cross that one off the list. But if you have sites which are showing some reasonable trends, then you need to identify the attribution factors. It can be a global warming signal, which is embedded in your time series. It can be anthropogenic signal. It can be a climate variable. Of course, that can be easily evaluated. So, for example, if the flows or rainfalls are affected by ENSO, then you can pick up the three states of ENSO: the neutral, the positive, and the negative, or warm or cool phases and neutral, and then see if there is substantial differences in the extremes because of ENSO phenomena, and then we can actually check that one through your tests. So again, if is changing in your time series, which you can establish either by trend tests or change point tests or visual evaluation of the time series or metadata, you can establish that. Then you have to start seeking the attribution aspect of what are the things which are changing with respect to time within that area as auxiliary variables. That is what you have to do that. What we have done in the recent paper is that I should have somewhere, I will show that one. Meanwhile, any questions on what we have discussed today?
No
or
questions,
any other questions?
Only Aarti is typing ADF test.
Yes. What is that?
Yes, actually that was in continuation with that Kpss test. So just I wrote that ADF test.
Okay, so what is? Can you give me the full form? My mind is drawing the blank. We recently used in a paper also. What is that?
Augmented Dickey-Fuller test.
Yeah, Dickey-Fuller test. Sorry.
Yes.
Right, you're right. Augmented Dickey-Fuller test. So these are very unique tests for econometric time series, but they work for our time series also. Limited number of people have used these two tests in trend analysis, especially to show that whether the time series has a unit root process or not. That means a time series can be modeled using a specific autoregressive model or not. So both of the tests will rely on that. They do have some limitations. And none of these tests will check for the strong or weak or stationarity. So that is what is very critical when we are trying to understand the problems associated with non-stationarity. So let me see if I can find let me see if I can find that somewhere. I should have that. Give me 1 second. Okay, I will find it here. Okay, this should be the process. I don't know if you guys have read my recent paper, but that is, let me share the screen with you guys first. Entire screen. So this is, this gives us the random block approach. So what we have done is we started with the time series. We make them into small blocks, and then we test the properties against each other. It can be equal block or unequal block. So these are the slices of your time series. Okay, and then we test for strong and weak stationarity. And the other approach is that when we divide them into blocks, we get either a mean value or one of the values for that particular time block, or we can pick up one of the statistics, skewness, kurtosis, and then we see if there is any trends in that data. So that means mean is changing over the time because these are chronological blocks. Again, the same thing with that. So this was one of the papers where we discussed the stationarity concept and how to comprehensively test stationarity, and then sometimes, yeah.
Aarti has shared your paper in chat box.
Okay, so yes, so I can
Non-overlapping block stratified random sampling approach for assessment of stationarity?
Yes, yes. So that was with Dr. Sharma. He worked with me as a postdoc. So again, this is something notes I prepared. So there are different ways of defining stationarity, you know, weak stationarity, strict stationarity, nth order stationarity, cyclostationarity, trend stationarity, and so on. But stationarity is required for all kinds of models, including time series models. If you want to develop a time series model, stationarity is the first thing, because if your time series is not stationary, then you'll not be able to develop any time series forecasting models. So what they do in time series models is that they try to do a difference of the time series. For example, the first one is a random walk series. A random walk series is nothing but you start with one number and then you add a random perturbation to that and use the next one. So each value is dependent on the other one. So therefore, there's a very strong correlation. So autocorrelation. So now we can difference this time series and we get completely a series called first difference series. And then you can do a second difference series. So what we are doing is, by doing the difference of the series, you are basically removing the autocorrelation structure of your data. Okay. So for example, this is your monthly temperature data. And you see that a nice cycle of your temperature data, because the temperature increases every year in the summer and goes down. This is the mean value of every month. And you can remove the, you can deseason the data. So when you remove the deseason, this looks like this. You can remove the trend also. Then deseason and without trend. And then you will see that autocorrelation completely drops, and then that series is now ready for development of a autocorrelation, autoregressive moving average models or any time series forecasting models. Because when you remove all the components which are affecting the time series, which might result in a non-stationary behavior into the future, if you remove all those things, then only you can develop a time series forecasting model. So that is an example of that. So remember, we were saying that we will try to define the blocks and then try to find out the characteristics. See, 3 large blocks, different distributions. So that's one thing. I don't know if we have an example of a stationary time series here. I have some trends. This is monthly variations, even though you see not much change in the distributions and not much change in the 3 time series or sub-slices. This is a perfect example of another temperature time series where we divide it into 2 sub-series. They have a similar statistical properties. That is the difference series, and we are trying to show that there's no autocorrelation. The first one is a Gaussian random noise. So you can see the Gaussian distribution, no autocorrelation at all. Random walk, and very high correlation. So that's what it is. And of course, we did some other analysis, try to understand the data sets with Monte Carlo simulation to generate synthetic series and then check our approach if it works or not. So as I said, the attempt was to see if we can find out a generalized approach for assessment of the stationarity. It's only purely assessment of the stationarity, not the attribution part. Why that is happening, it's completely difficult for us to come up with a specific reason. Okay. Any other questions?
No questions, sir. So thank you very much. Throughout the day, you have kept us learning newer things, and that too in a very simple way. I hope that today's presentations will be very much useful to all the scholars who are attending this particular sessions. So I thank you very much, sir, and we'll stop here for today. And tomorrow again we will meet. I think, sir, you have your lecture is scheduled at 5 p.m. tomorrow.
Tomorrow at 5 p.m. right? You said?
Yeah.
Okay.
And in the morning at 3:30 p.m. we have Sanjay Kumar Jain from NIH
Sure.
Roorkee. He is a director and nodal officer for National Hydrology Project
Sure.
of India.
I know him very well, so I will attend that, and then you have another presentation tomorrow, or I think
3:30 p.m. we have presentation of Sanjay Kumar Jain. 5 p.m.
And then
your presentation, and last session I'm going to discuss about case study of Girna River Basin. Okay.
You are discussing that tomorrow. Okay, good. So thank you all, and keep all your questions. You know, we can always answer on the next day or day after. Okay, so we can do that. Thank you so much.
Please
go.
Stop presenting.
Okay.
I request everyone to switch on their cameras for attendance.
Please switch on your cameras. Dr. T, if you can, so that we will have your picture with all participants too.
Okay. Good. Let me see if I can get my.
Participant, you are lucky that you are having picture with Dr. T.
So, don't make me a celebrity. I'm not. Okay.
For us, you are celebrity, sir.
No.
Done, Rashmi?
Thank you so much, sir. It is done. Thank you, everyone.
Thank you.
Okay, so everyone.
Thank you.
Thank you so much.
We'll see you all tomorrow.
Tomorrow.
Yeah.